Hello everyone. Thank you for attending today's Watershed webinar, Assessing Impacts to Local Streams. Our presenter is Mr. Jim Eckenrode, Engineering Lab Manager at St. Francis University.
Okay, great. Thank you, Michael. Bring up my presentation. Okay, as Michael said, my name is Jim Eckenrode. I am the lab manager for the engineering department here at St. Francis University. And prior to that, I was a watershed specialist for about 18 years. My specialty, I suppose, is field work and stream evaluation and the work that goes into that. So I think this will be, hopefully, it'll be a great presentation. And today, I'm definitely going to do it a little bit different. We have some videos that we'd like to highlight that our students have made that I think will be really great tools for you to use in the future. And those will be available during the presentation. I'm going to show them. Also be available in the chat for actual links if for some reason you can't see my presentation. And then of course they'll be available after the presentation also. So let's go ahead and get started. Again, so we're going to discuss today assessing the impacts to local streams. One second. Okay, great. So how do we evaluate streams? Or why do we evaluate them and how do we evaluate them? First, why do we evaluate them? So basically, we want to make sure a stream is meeting its best possible use. And that's the reason why we evaluate them. And we evaluate them to develop a baseline water quality data, or to develop baseline water quality data. So that can be used to determine if a stream needs restoration. It can be used to characterize a stream in case of a bad pollution event or a pollution event. And the reason we do that is because both the state and the federal agencies, if there is a pollution event, they will look at that pollution, they will look at that change to the stream. And that change is often how they determine the amount of the impact or the breadth of the impact. And then also, if any fines are levied, they often use that information. And third, what do we determine that we have a really high quality stream and we need to make sure that it's properly protected. So that's why we evaluate streams. If you haven't heard these terms before, the state does identify streams according to Chapter 93 as the following. So we're going to go from not necessarily poor quality streams, but poorer quality or quality that affords less protection. And we can talk about why throughout the presentation. But we have warm water fisheries. So at the bottom right, you see TSF, trout stock fisheries, cold water fisheries, cold water fisheries, HQ or high quality, and then EV stands for exceptional value. EV being the highest designation, the most protection, and WWF, warm water fishery, being the lowest level of protection. So I showed these two photographs in my last presentation. We have streams that look like this. We have streams that look like this. So how do we evaluate our streams? Whenever we do a stream evaluation, we look at three primary characteristics. We're going to look at physical characteristics. We're going to do that by habitat assessment. We're going to look at the chemical parameters. So that's going to give us our water quality. And then we're going to take that in conjunction with our flows. And we're going to use that to get loading. But we're going to look at the quality and the quantity. And we use those numbers to determine our loading or impact to our streams. And then we're going to look at macroinvertebrates. So again, physical characteristics, the habitat, the chemical parameters, the water quality, and then macroinvertebrates, which are the stream bugs.
Hey Jim, I think, is this the time where we're going to do the polling?
Yes, it is. Go right ahead.
Awesome. So what are the three characteristics used for, or criteria used for evaluating streams? Awesome. Everybody got it. Very good. I think they were listening.
All right, thank you very much.
Yes, thank you.
Awesome. Okay, so this should be more flawless as we move forward, but we're going to start with our first video. And the first video and the first criteria that we discussed is habitat assessment. You know, we did this yesterday and it worked just fine.
And we can't hear your audio. I'll put the link to it in the chat then. There it goes.
I've noticed that some of them create a better habitat than others. From polluted urban streams to pristine ones located deep within the Alps, the ability of streams to support aquatic life varies quite a bit. One way to scientifically assess this ability is through a habitat assessment form. Created by the Pennsylvania Department of Environmental Protection, the habitat assessment form rates various qualities of the stream like its flow rate, or the composition of the stream bed based on how apt it is as a home for aquatic life. Today we'll be looking at two streams. One is an urban stream sandwiched between two concrete buildings and a roadway. The other is a woodland stream near a biking trail. With this, the habitat assessment form will be used to rate the stream's ability to support aquatic life. The first category we'll be discussing is epifaunal substrate and cover. Epifaunal substrate and cover describes underwater structure, including fallen logs, large rocks, and undercut shores. Various fish and macroinvertebrates make their homes in these irregular structures. Let's first take a look at the urban stream. There's not much cover to speak of here in terms of fallen logs or anything of the sort. The only thing that may be used as structure is the rocky bottom, which could house some macroinvertebrates. However, this is largely insufficient as a cover for an entire ecosystem. Verdict, poor, 3 out of 20. Looking at the woodland stream, there's a decent amount of cover. The left side of the stream is consistently undercut due to erosion, providing a hiding spot for fish and macroinvertebrates. Also, the stream bed has a decent amount of cobble, except for in deep pools, and has some fallen logs. However, large rocks and other forms of cover are somewhat sparse. Verdict, suboptimal, 15 out of 20. Now let's talk about pool substrate characterization. Pool substrate characterization refers to the composition of the stream bed in deep, slow-moving pools. An ideal stream bed is composed of rocky bottoms where organisms can live and some aquatic plant life, rather than just mud and silt. The urban stream has no plant life present. The stream bed is filled with cobble. In fact, cobble covers most of the stream bed, but this cobble is shallow and covers a layer of silt and mud. Verdict, poor, 5 out of 20. The woodland stream also has little to no plant life. In addition, most of the deep pools are barren or lacking in cobble. As a result, dirt and silt is often exposed on the stream bed. Verdict, marginal, 7 out of 20. The next category is pool variability. Pool variability rates the level of variety of the pools within a stream based on both size and depth. In terms of pool variability, there's really none to speak of for the urban stream. Both the size and depth of the urban stream are virtually uniform throughout, likely due to the surrounding neighborhood which has altered the stream. Verdict, poor, 0 out of 20. Looking at the woodland stream, there are a few medium-sized pools. However, these pools are lacking in variety in terms of both size and depth. So my verdict is marginal, 6 out of 20. Next, sediment deposition. This refers to harmful buildups of sediment mounds, like in the picture shown. These mounds are detrimental to the flow of the stream as well as to the quality of the stream bed. Sediment has accumulated in small piles throughout the stream bed in the urban stream. Sedimentation has affected 50 to 80% of the stream bed. Verdict, marginal, 7 out of 20. Now, while it hasn't caused any large buildups here, slow-moving parts of the woodland stream often gather some sediment on the stream bed. Sedimentation has affected 20 to 50% of the stream bed. My verdict is suboptimal, 14 out of 20. Let's now move on to the next category, channel flow status. This measures the degree to which the stream channel is filled with water. Streams that do not fill most of the available channel are said to have a low flow rate. We can see that in the urban stream, quite a bit of the stream bed is exposed. Roughly speaking, anywhere from 50 to 75% of the stream bed is left barren. As a result, my verdict is marginal, 8 out of 20. Now for the woodland stream. The stream channel is largely filled and has a steady flow rate. However, the water level has gotten somewhat low, likely due to consistently dry weather over the summer months. It has been a very dry summer. Verdict, suboptimal, 14 out of 20. And now let's move on to the next category, channel alteration. This measures the impact people have made in changing the path of the stream. For example, many streams are straightened or deepened in order to prevent flooding. In terms of the urban stream, I think this one's pretty obvious. The entire stream is lined with 2 cement walls. The stream even flows underneath a small bridge that cars drive on and goes underneath buildings. Also, the channel has been altered to make the stream flow in a straight line. Verdict, poor, 1 out of 20. Now, the woodland stream has had its path accommodated for the formerly active railroad tracks and brickyard factory, as well as a modern biking trail near the stream bank. As a result, the stream has less natural bends and turns throughout its run. Verdict, marginal, 7 out of 20. Our next category is bank stability, which measures the degree to which the stream bank has eroded or has the potential to erode. For the urban stream, there really is no bank, just cement. Technically, the cement itself would be stable from erosion, but the fact that there is no stream bank is very detrimental to the health of the stream. In addition, surrounding lawns and properties are not necessarily free from erosion. Verdict, poor, 0 out of 10 on both sides. The woodland stream has experienced some significant bank erosion, particularly on the left side. The left stream bank shows clear signs of erosion, as the steep cutoff and exposed dirt shows. The right side, however, has a gradual slope up and into the riparian zone while still showing some signs of erosion. Verdict, marginal, suboptimal, 6 out of 10 on the right side. Moving on, let's discuss vegetative protection. As the name suggests, vegetative protection describes the degree to which the stream bank is covered with vegetation. It can also be thought of as how dense the vegetation is. The plant life filters out harmful pollutants, which would otherwise find their way into the stream. Looking at the urban stream, the nearest plant life is all the way on top of the concrete and into people's yards. As opposed to native plant life, there are green lawns and sparse shrubbery. It will do very little to filter pollutants. Verdict, poor, 1 out of 10 on both sides. Looking at the woodland stream, there is a dense cover of trees and other vegetation on both sides. However, some of this plant life includes invasive species, including knotweed. However, there is enough vegetation to act as a fairly effective cover. Verdict, suboptimal, 8 out of 10 on both sides. Last but not least, we have the riparian vegetative zone. Not to be confused with vegetative protection, a riparian vegetative zone describes the width of land directly adjacent to the stream bank that is covered with vegetation. Again, for the urban stream, this is a bit tricky to classify since there really is no stream bank to speak of, just 2 concrete slabs. The plant life on top from people's yards hardly stretches a few meters before being met with a concrete road. Verdict, poor, 0 out of 10 on both sides. Now the left side of the woodland stream has a large riparian zone. It stretches as far as I could see from where I was filming. It does intersect with a neighborhood about a quarter of a mile down. The right side intersects with a biking trail after a few meters. This trail, however, is fairly low impact. Verdict, optimal, 9 out of 10 on the left side, suboptimal, 8 out of 10 on the right side. Alright, now let's add up the scores for both streams. For the urban stream, we have a score of 26 out of a possible 180 points. Ouch, this stream is not a very suitable habitat. In contrast, the woodland stream has a score of 105 out of 180, which by no means is that an ideal stream, but unsurprisingly, it's better off than its urban counterpart. The next time you are at a local stream, think about some of the criteria in the habitat assessment form and ask yourself, can aquatic life survive here?
Okay, great. So I really love that video because Kevin does an excellent job of going through the habitat assessment. The habitat assessment is a phenomenal tool because it's free. It takes nothing but your time and your perspective to go and fill that out. And there really is value in that tool. Those categories, that habitat assessment is part of the rapid bioassessment protocol from the EPA. And it's great for students to go out. It's great for them to talk about the different impacts of the streams, embeddedness, looking at the stream substrate, looking at the riparian zones. And it's really nice to do before and after a project too, so they can see how simple improvements, maybe a riparian buffer planting or maybe felling some trees for habitat, just how small projects can make a big difference in the habitat of a stream. So again, one of my favorite assessment tools, very inexpensive to do, and it works really well. Right. Are there any questions? Does anybody have any questions about that video or the assessment tool? Okay. Move on. So next, criteria. How do we evaluate streams? Now we're going to look at chemical parameters and flow. So we're going to look at the quality of the stream and the quantity of the stream, or quantity of the water in the stream. Let's first talk about what's the first thing you do when you go out to a stream to evaluate for chemical parameters. You're going to look at your field parameters, and those are pH, conductivity, dissolved oxygen, temperature, and flow. So I know this is a little bit rudimentary for some, but I do want to just quickly review those criteria. So what is pH? Well, pH is a measure of hydrogen ions in solution. I think we all know the scale for pH goes from 0 to 14. 7 is neutral. Anything less than 7 is considered acidic. Anything greater than 7 is basic or alkaline. Water quality standards for a natural stream are going to be between 6 and 9. Some species can go down to 5.5, and some species, most fish species actually around 8.5. But the water quality standards in Pennsylvania are between 6 and 9 pH. Specifically, brook trout, our native trout, prefers 4.5 to 7.5 pH. I would say 4.5 is pretty low. It's probably more like 5.5 to 7.5 pH. Okay, so conductivity. Conductivity is recorded in microsiemens per centimeter, and it's just the ability to pass electricity through water. So if you had, and that includes anything that would cause electricity to be able to be transferred more quickly. So any kind of, anything in the water that could help that happen. So you're talking about metals and salts and sediments. So to give you an idea, if you had distilled water, conductivity could be very low, 0.5 to 3 microsiemens per centimeter. In contrast, just to give you an example, Marcellus Shale flowback water, which is often discussed as something that is, one, very salty and could be a problem. You could be looking at 80,000 microsiemens per centimeter. So big difference. And to put that in perspective, water quality guidelines for a freestone stream are between 40 and 120. And for a limestone-based stream, they're between 100 and 250. And that's because with the limestone-based streams, the geology is adding additional connectivity into the stream with your manganese and calcium and stuff like that from our local limestone. Dissolved oxygen. Dissolved oxygen is simply the measurement of available oxygen in water. Dissolved oxygen concentrations are directly related to, of course, the movement. If you have a lot of gradient and there's a lot of rolling of the water, that movement can add additional oxygen in the water, and the temperature of the water. And of course, we know temperature and dissolved oxygen are very closely related because as the temperature increases in the stream and the water, the amount of oxygen the water can hold decreases. So again, back to some of those water quality standards, cold water fishes prefer, so when I speak of cold water fishes, I'm talking about our trout, our brooks, our browns. When when we speak more about warm water fishes, we're talking about our bass and our panfish and stuff like that. In general, we try to focus on cold water species because they are a native species, and we'd really like the highest quality water possible. So for dissolved oxygen, cold water fishes prefer greater than 6 milligrams per liter, and warm water fishes can go down to just 1 milligram less and 5 milligrams per liter or greater. So good thing is, in most of our streams that have flowing water, we're pretty good about keeping dissolved oxygen concentrations that high, but I have seen it drop down below 5. Okay, so water temperature. So temperature obviously directly affects water chemistry parameters as well as the fish themselves. Warmer water can affect the rate of biological processes and cause lactic acid buildup in cold water species. So the two guidelines for water temperature are less than 30 for warm water species and less than 18 or 19 degrees Celsius for cold water species. So basically, cold water species don't really want to be in water warmer than 65, and warm water species 85 to 90, and that's going to be their max. And what happens in addition to some of the side effects with the way they take water in and out of their bodies and the oxygen, they when cold water species get too warm, they become lethargic. They'll start to look for pools of cooler water. After that, if it gets a little bit warmer in the mid 70s, they're going to slow down. They're going to stop eating. They're just going to be hanging out. And you get up in the high 70s and low 80s. That can be lethal for some of our cold water species if you're talking about multiple days in a row. Okay, so let's talk about equipment. That's the other component that I wanted to speak about today. So how do you do these assessments? So in your photograph here, you have two instruments, the small black meter with a yellow lanyard, and then the blue meter. Together, these two meters cost about $620, $650. They're actually fairly reliable and fairly accurate. The black meter is going to do pH, temperature, conductivity, and TDS. And the blue meter is going to do your dissolved oxygen. I think the black meter does an excellent job. The blue meter does an excellent job. Together, they give you all the parameters that you need for your field parameters. One note is that I think the pH on that black meter does tend to read a little higher, but it is consistent. So that's nice at least. But don't ever be afraid to double check your equipment against another piece if you have that opportunity. So that was the $650 option. This option is a $3,000 option. This piece of equipment does the exact same thing: pH, conductivity, temperature, dissolved oxygen. It is a little bit more accurate. It is very reliable. It can also store the data if that's something that you'd like. But you do get an upgraded dissolved oxygen sensor in this unit, and it's a luminescent DO, and it will last a lot longer, be more efficient for you in the long run, and you'll have to replace it. The ones used on the other unit do need replaced often and calibrated, where this actually can almost never be replaced for years, and does a pretty good job of holding its calibration. But again, it's obviously, what, 3-6 times more expensive. So, or at least 5 times more expensive. So how accurate are they? So this is a comparison of the two units to each other. I'm not saying that one unit is more accurate than the other, but what is the difference between the two units? So the parameter that had the biggest error or change difference was the percent dissolved oxygen. pH is next at 4.5, roughly 4.45. But you'll notice conductivity and temperature are going to be excellent parameters. You're going to get very good information. and you're gonna get reliable information. And honestly, even at 4.85% or 5%, your DO sensor, regardless of whether you spend $600 or $700 or $3,000, can be very reliable. So for those people who want to deploy this in their classrooms or whatever, you do have some options. And this is my plug. You should never take your equipment out ever before calibrating it. So if you want your equipment to, if you want your data to be good and you want to have good working equipment, it doesn't take very long. Please always, always, always calibrate your equipment before going into the field. Okay, so now we're going to talk about flow. Flow is a little trickier. Why do we need flow? Well, flow can help document that seasonal change in quantity, or can address some consumptive use issues if that's a problem in your watershed, where where somebody or someone is taking a lot of water out of the system. It's really important for determining pollution episodes, whether they're, episodic, so they happen within a rainfall event, or if it's more chronic, always present, something seeping into the watershed or into the stream. And flow is the other half of that loading equation. So when you have your chemistry, which I'll talk about next, you're looking at, say, nitrates, and you're looking at milligrams per liter. Well, if you have milligrams per liter, but you only have, let's just say, 10 gallons a minute, your loading, your impact to the stream, may not be too bad. If you have that same concentration and you're dealing with 10,000 gallons a minute, that's a much bigger impact to the stream. So, and I'll talk a little bit more about loading. Okay, so what do you need to take a flow measurement? Well, this industry standard is a flow tracker. It's an acoustic Doppler velocimeter, or velocity meter, and it's about $8,000. And honestly, it's probably a little bit more than that, maybe closer to $9,000 today. It's very easy to use, but it is time consuming. So every measurement you take, every stream location, every sample that you take, it'll take you about 45 additional minutes to collect a flow. So just take that into consideration. Here's one of our students conducting a flow. Basically, you take a tape measure, you stretch it the length of the stream, and you're looking for two things here. You're looking for velocity. That's what the meter is recording. So the speed at which the water is passing past a certain point, that velocity, in either meters per second or feet per second. And then you're also looking at the area. So every single measurement, you're taking a width, and you're taking a height of the water. So you're determining how much of that channel is filled with water, and that gives you your area. Another option you have to do flow, if it's a site that you plan to visit a lot, especially for schools, you might be able to set one of these up, is you could install a staff plate. Staff plates are pretty cheap, a couple $100, maybe not even. You might go, if you have the tools already, you could probably get away with less than $100. And what you're going to do with a staff plate is you're going to determine stage. So it's that water height or that water level. The numbers on that plate are arbitrary. They don't represent anything like, so many feet above sea level or anything like that. But they allow you to record, in this case, feet, the change of the water level. So using those numbers, and then using the numbers you collect with your flow meter, you get about 12 samples. You can then apply a regression equation, and you can develop a hydrograph for your site, where you would have discharge in cubic feet per second on one axis, and then you would have this height on the other axis. And then once you plot that curve, you can then go, okay, as long as nothing's changed, a huge flood didn't come through and change the channel too much, you can go, today I have 2.2 feet on my staff plate. and that equates to 64 CFS. So once you develop that hydrograph, and it doesn't take that long, you just need to make sure that you have a good diversity in flows, so like high flows and low flows. So you're not trying to extrapolate below or beyond the data you have. You can collect really good data that way, and it makes it so much easier to take flow measurements. All right, so if you don't have an $8,000 meter, what do? Well, I have another video for you. We're gonna try this out.
Flow rate is defined as the volume of fluid flowing through an area each second. Stream flow rate is important because of the impacts it has on water quality and on living organisms and habitats in the stream. Larger, fast-flowing rivers can receive pollution discharges and not experience as severe effects, whereas small streams have less capability to dilute and degrade waste. Stream velocity, a component of stream flow, determines the kinds of organisms that live in the stream. For example, some animals need fast-flowing areas, while others live in quiet pools. Flow rate can also affect the amount of sediment carried by the stream. Sediment in a slow-flowing stream will settle quickly to the stream bottom, while sediment in a fast-flowing stream will be suspended longer in the water column. Additionally, fast-moving streams generally have higher levels of dissolved oxygen as compared to slow streams, because fast-flowing streams are more aerated. The following example demonstrates the simple way of measuring flow rate in a stream.
Today I'm going to show you how you can measure stream flow with a few household objects. First, you're going to need some twine or some string. You're going to need a measuring tape and a buoyant object like a piece of fruit and a stopwatch. So the first thing we're going to do is we're going to set up our string or twine or rope or whatever material you have. And you want it to span across the entire stream. And you want two sides of it, because this is going to block off your area that you're measuring the flow in. So I just tied it to some sticks, but I tried to make it pretty parallel. So now that our twine is all set up and our area is established, we're going to take our object, like our piece of fruit, I have an orange, and I'm going to let it flow from one side of my twine to the other. And I'm going to time how long it takes. So I'm taking my buoyant object, I'm going to drop it on the outside of my twine, and I'm going to start my timer when it is directly under this side, and I'm going to end it when it's directly under the opposite side. And that's how much time it takes for my orange to get from point A to point B. Alright, so that took roughly 9 seconds. I'm going to repeat this process after I get my orange, and I'll take an average of those times for my time in my flow rate. Okay, so now I'm going to use my tape measure to measure the area of my stream, this cross-sectional area here. So first I'm going to measure the width of the stream, and then I'm going to measure the distance between my two pieces of twine. So now I'm going to take a few depth measurements so that I can take an average of them and get an average depth. So that way I can find a volume and then divide by the times that we have. So now that we have our depth measurements, we have our two measurements for our area, and we have all of those time measurements for our object to float through. I'm going to show you how you can calculate flow.
On the right side of the screen, you can see a list of our field measurements. The equation we are going to use to calculate stream flow is flow rate equals length times width times depth divided by time. Length times width times depth is the same thing as volume. The first thing we need to do is determine our average depth and our average time. The average depth was found by adding up all of the depth measurements and dividing by the number of measurements. The average depth was found to be 3.17 inches. Similarly, the average time was determined by adding up the time measurements and dividing by the number of measurements. The average time was found to be 9.05 seconds. The next step is to plug our values of length, width, depth, and time into our flow rate equation. After subbing in our known values, we can now calculate the flow rate. Our flow rate was found to be 3,606.4 cubic inches per second, which is equal to 2.09 cubic feet per second.
Okay, so like Kevin and Carrie did a great job. I love the fact that you put the equations right up for everyone to see. I think this would be a really good, valuable tool for you to use in your classrooms. And does anybody have any questions? So it's the same math, regardless of the equipment that you're using. You're looking at volume, you're looking at velocity, and you're basically determining the standard units would be cubic feet per second. Anybody have any questions or comments? Okay, great. Okay, so we're still working with our chemical parameters. So we looked at the field parameters, pH, conductivity, dissolved oxygen, and temperature. We looked at flow. Let's finish our chemical parameters off. So I didn't go into in-depth like I did for the previous ones, but some of the common parameters people are looking at when they're trying to evaluate their stream are nitrates and phosphates and sulfates, alkalinity, turbidity, and then some people are looking at ions. So you're looking at all your metals. You know, if you're looking at mine drains, you might be looking at iron, aluminum, manganese. If you're looking at urban runoffs, you may be looking for other metals, zinc, copper, stuff like that. So there are a lot of ways to do that, and you just need to basically start with your list, or maybe you look at your influences, maybe where your pollution's coming from, looking at some of those characteristics and determining what chemical parameters you'd like to look at. So then how can you do analysis on it? The easiest way to do it is both Hawk and Lamont make these color comparator test kits. The test kits turn out to be about $55-ish a parameter. They're easy to use. They're meant to be replicated. But in this case, the color comparator ones, where the student or the person in general is doing the determination on color, the one wheel for alkalinity is like 17 different shades of pink. So, it may look one way to one person and different to the other. So these are good kits. They work well, but they are a bit subjective. Next level would be a colorimeter. Same blue kit, same manufacturer, but these kits, the colorimeter does that analysis for you. So it determines the change in the color, which is then recorded in milligrams per liter usually of whatever you're looking at, whether it's nitrates or phosphates, again, or metals. Colorimeters are great. These pocket colorimeters cost about $1,000, but they can do 80 to 90 different tests. So then you just need to buy the reagents for the test. And the reagents are not inexpensive, but they're usually $30 to $40 for the reagents, but that's for 100 tests, usually for each reagent. So the colorimeters are actually a really great resource. Okay, finally, I just want to cover sample collection. Say you don't have access to the colorimeter and you want to send a sample to a lab for analysis. There are two types of samples that you'll take, a grab sample or a composite sample. Grab samples, as the word says, pretty simple. We're going to walk up to a stream. you're going to put your bottle into the stream, and you're going to choose the site that is about midstream and mid-depth. And the grab samples really work best on first and second order streams. A composite sample is where you take a bunch of samples, mix them all together, and then you take your sample for the lab out of one container. Just take into consideration some samples, like your petroleum products, your oils and stuff like that, cannot be taken in a composite sampler because you end up getting some of your sample will stick to the inside of the container, and then you'll lose that analysis, that concentration from your sample. So here's an example of some equipment you would use for a composite sample. So the narrow bottle with the tip on it is the item that you would use to work your way across the stream. And you would insert the bottle on the wand into the column and lower it down gently, and then pull it to the top. Step over a foot, and you just work your way across the stream so that you sample the entire column. And then when you're done with your samples, you'd fill that bottle up, depending on how much water you need, a couple times. You would incorporate all of them into that, basically, which the churn looks like a Kool-Aid jug. Then you would take your sample out of that jug, and that's how you get a composite sample. Finally, at least in this category, I want to cover the idea of a sample sheet or a site summary sheet. I think these are really valuable to students, especially because you're going to be going from year to year to year and class to class to class. Plus, I think if you look at one day's worth of data, it doesn't give you a whole picture. And I love these site summary sheets because they do that well. I made all this up. You can feel free to use any of it or none of it, but I like to include the name of the stream, your GPS coordinates, the major watershed. I like to include the dominant geology. So again, is this freestone or is this limestone influenced? I like to include the state stream designation. In this case, it was a cold water fishery. Land use percentages, so is it forested, agriculture, or urban? And then as you just work your way down the data sheet, include everything that you're sampling. If it's 3 items or 10 items, include them all. pH, conductivity, dissolved oxygen, nitrates, phosphates, sulfates, iron, temperature. And then I do min, max, and average. And then for educational purposes, I also put in the last column the standards. So the pH, average for this site was 7.24. It should be between 6 and 9, and it is. So I didn't do these sheets for years, and people would ask me about a site, and I'm like, oh, I've been to so many, I can't remember. I don't know what it looked like last year. I love these sheets. They really have become invaluable in characterizing in one sheet the stream well after you visited a couple times. Great resource. Okay, so 2 more items, but one more item under chemistry. I just want to introduce this idea of continuous in-stream monitoring. What does that mean? Continuous in-stream monitoring is done by a piece of equipment that's deployed in a stream that will record data in some very small interval. That interval can be a minute, 5 minutes, 15 minutes, an hour, whatever. But it's the idea that this instrument is taking recordings on whatever parameters you would like continuously. So you're not getting a single snapshot. You're not going out once a semester, grabbing a sample, and then trying to use that sample to characterize the stream for a whole year. Continuous in-stream monitoring is a fairly new resource or product available, and it works really well. And you can use it for analyzing trends. You can use it to identify fluctuations that maybe are happening when you're not there, maybe during storm events when it's not safe to get into a stream, or maybe in the middle of the night that only happens to be happening in the evening. So it's a really great idea if you're able to do it. Some of the downfalls of continuous in-stream monitoring can be crazy expensive. The pieces of equipment are usually around $3,000 to $8,000, depending on the parameters that you're looking at. It can be time consuming. They do take maintenance. And I think the most important part is that they can create a ton of data. If you think about how many samples or how many results you're going to get if you deploy a sonde in a stream for a 30-day period at 15-minute intervals, you're talking over 4,000 entries. So you need to be prepared to figure out how you're going to manage those if this is the route you'd like to take. And here's just some of the equipment you might find useful or that is available for in-stream monitoring. The stuff on the left of the screen, $1,000, $1,500, very inexpensive. You know, 2 parameters, you're usually going to get stage and temperature. Some of them can do pH. As you work your way in the middle and towards the right of the screen, those instruments can cost upwards to $30,000 a piece. So again, it just depends on how important this data is and how much potential resources you have and money and time to move with something like this. These are nice, you know, if a school or a location is able to purchase some of this equipment to deploy for a long time and to see changes over years. So they are really nice for that. And here's just an example of some data. So this is one site that I had on the Little Juniata for 10 days in May. The yellow is the turbidity. So you can see that the concentrations in turbidity are going up and down and fluctuating. And they're almost exactly at the same times as fluctuations in the stream. The blue line is stage. So as you see the stage increases, so during a rain event, the turbidity is increasing. And I just love these graphs. So this data is so much fun to work with and it's really, really a great resource. But like I said, can be cost and time intensive. Okay, so I'm going to go on to the last item for evaluating streams, and that's macroinvertebrates. And I have a one more video. And this is really just to give you some exposure to macroinvertebrates. There are some different resources available, phenomenal books, flashcards on identification, and there are so many metrics that you can use to quantify macroinvertebrates to determine stream health. I didn't address them all. I just want to give you a little bit of overview. So, one second, I have one more video.
Macroinvertebrates are invertebrates that can be captured by a net or sieve. There are various types of macroinvertebrates such as insects, mites, scuds, and crayfish. Macroinvertebrates are good bioindicators that determine the quality of water. Macroinvertebrates are affected by the physical, chemical, and biological conditions of a stream. These aquatic invertebrates cannot escape pollution, so different types of macroinvertebrates can tolerate different amounts of pollution. We can then sample these invertebrates to obtain a better understanding of a stream's health.
We're going to do some macroinvertebrate sampling here with our D-net. And what we're going to do is we're going to plunge the net in the water and then kick the rocks. And by kicking the rocks, we're moving the soil or the bottom of the creek into our net, which our macroinvertebrates are at. And as you see, we're working upstream. When we work upstream, we're not tampering with our possible catches.
The macroinvertebrates that were captured by the D-net were then placed into ice cube trays with water. Some of the macroinvertebrates that were found in this stream were a crayfish, a dragonfly nymph, a midge larva, a mayfly nymph, a caddisfly larva, and a hellgrammite. It is known that stoneflies, mayflies, and caddisfly larvae cannot survive in highly polluted waters, so we can conclude by our findings that this is a healthy and non-polluted waterway. We also want to mention that all of our found species were safely released back into their natural habitat that they were found in. This stream makes its way to the Chesapeake Bay. By this stream being cleaned, it lessens the chances of the Chesapeake Bay becoming polluted. A stream that is full of pollution would have macroinvertebrates such as blackfly larvae, midgefly larvae, and lug snails. These macroinvertebrates have a high tolerance to pollution and can survive in these toxic waters. Sometimes a waterway may lack a variety of macroinvertebrate species, but that does not mean that this water is unsafe for these creatures. That is why tests like pH, dissolved oxygen, and alkalinity are taken and observed to assess the stream.
So, Mr. Eckenrode, I'm going to do our other poll here. So everybody hopefully can see that. I hope I see John had some audio issues. I hope that things are working okay for everyone. If not, we'll share the links there to the videos. We are coming up on the end of the hour here. So we'll be conscious of that, but maybe we'll take some time to finish up here, and then we can take some questions, and I will get the Act 48 form up here in a moment. So it looks like we've got, everybody said yes, some critters are more sensitive than others, which I believe is accurate. So thank you.
It is, Michael. Make sure, okay. So that is, and I do apologize. We did fill a whole hour just with that. I do have some time to answer any questions if there are any questions. I think that was a really great introduction to the characteristics that we use and to identify streams, and some good examples, some videos, some resources. Of course, anybody can feel free to reach out to me at any point in time. The way I was sharing with the video, I could not see the chat. I can now. But if anybody has any questions, I'd be glad to answer those. And if not, again, as I said, feel free. You can reach me at St. Francis in the engineering department. I'm sure Michael will provide everybody with our contact information. And I do greatly appreciate your time.
We did have a question about any additional resources for simple, affordable monitoring for upper elementary students.
Sure, I was just reading that. Thanks, John. The answer is yes. I tried to give a few examples. There are some kits that are less expensive and good for introduction. We have some resources available here. I think Michael could help you identify some of those. If you had a specific parameter that you're looking at, it would be easier for me to identify one. Feel free to reach out. But we do have other videos, and we're having more videos to come. There's a video on alkalinity. There's a video on phosphates. And we have about 4 or 5 more after that. And they should all be coming within the next couple of weeks. So plenty of time for you to plan for next year. And Michael will reach out to you guys when those are available.
Do you have any other questions or anything that anybody is interested in right now?
Okay, then I will say, great. Again, thank you for your time. I hope this was helpful. This video will be put up when Michael gets those completed. You also have the slides at the end of this presentation, if you're interested. I've got about another 10 or 15 slides specific to some of the chemistry that we were discussing, related to nitrates, phosphates, how they may impact the stream and stuff like that. It's a good starting place for some information like that. And I'll let Michael take over. Thank you.
All right. Well, thank you everyone for attending today. We really appreciate you being here. If you have any comments, I know that there were some audio issues there. If you could provide any feedback on, whether or not that worked for you, I'd be interested in hearing that, as we're kind of new to that space. So if this is something that you think worked well, please let us know. If it's something you say, not so much, we'd love to hear your thoughts on it. But with that, hopefully you're able to see the assessment form there in the chat. And I will wish everybody a great day. Remember to join us for our up next 2 sessions. There's our email if you have any questions, and the website to find out more about the next session. So have a great day, and thanks everybody. See you later.